Hey there, this is Kirby Wadsworth. I'm the CMO at Ioneer, and welcome to another presentation, this time on the technical aspects of the Ioneer Kubernetes native storage platform. Hopefully you find this as interesting as some of the other ones that have been done earlier. We talked briefly prior to this about the why of Ioneer. The ability to move data quickly from one place to another to provide data agility in light of the Kubernetes environment, and to eliminate the impact or the effects of what we now know as data gravity. Today, I'm going to talk to you a little bit about how we do that and show you some examples, hopefully at a level that's easy enough to understand for everyone, how this magic actually happens. So just as a quick reminder, what Ioneer is a Kubernetes native storage platform. It is a container native storage software solution. We are not, as we always say, the only one in the marketplace, but we believe that we are the best, and we are differentiated in three very specific ways. First, the ability to move data from anywhere to anywhere instantly, literally in 40 seconds or less. We can move full volumes from one place to another. The ability to access data at any previous point in time in much less than 40 seconds, just in a few seconds, actually. We can access a full volume regardless of the size of the volume as it existed 1 minute or 1 day or 1 second ago. And then the final one is really the fundamental differences in the way that this product has been built. The team that built this built large enterprise storage systems, what we used to think of as big iron storage, for many years. Most of us have decades of experience in this particular industry. So this product has been built to the specifications and expectations of an enterprise class storage platform. It's also been built using Kubernetes architectures and Kubernetes approaches. So what we've done is we've combined the solidity, the weight and heft of a enterprise class storage platform, of course it's in software, with the extensibility, the flexibility, the future proofing of a Kubernetes microservices application. Pretty cool. All right, let's get into it. As I mentioned, the platform itself is a software-defined storage and data management platform. It operates in Kubernetes. It is written in Kubernetes. It is orchestrated by Kubernetes, and it serves Kubernetes applications as a set of services. We have physical storage that we get from somewhere, usually in the servers that are running the Kubernetes nodes, but it really could be from anywhere. We collect that together into a virtual pool, and then we present logical volumes out to the applications that require the capacity, the storage capacity. So in that, we are a very familiar kind of container native storage virtualization platform. As I said, there are unique characteristics, however, in the data and storage management layer. When you take the control plane and the data plane and separate them like we have here, it gives you the ability to do lots of really exciting and interesting things in between the two. So the first thing that we do, as I mentioned, is continuous data protection. This is the ability to store data and go back in time, any previous second. The ability to move data from one place to another in literally seconds, to break the laws of physics, if you will, or bend them. We have global dedupe built into the system already. We get it sort of organically, and you'll see that in a second. And we also provide automated tiering in the system so that we can maintain high velocity, high performance data on high velocity, high performance storage resources, for instance. But we do know from our automated tiering capability which portions of the volumes are hot and which are not. Very important and very useful, as you'll see in a moment. All right, let's talk about the architecture for a second. Look, the secret sauce in this sounds simple. It's not easy to do, but it's easy to understand. This is like a URL for storage. When the web came along, you would have had to know, before URLs, you would have had to know exactly what page you were looking for and where it was physically located. You would have had to put in a long string of numbers to indicate where you were looking for your data, because the data and the location of the data were combined into one addressing mechanism. The URL came along and broke that, and now we put in ioneer.com, and you don't know where ioneer.com exists. I don't either. But you know that when you punch in ioneer.com, you get the pages that we have presented up there for you to read and that you're interested in looking at. So this system does something very similar. Traditional systems have always integrated the location of the data that was being stored and integrated that in with the data itself. Ioneer breaks that by creating what we call a name, and I'm going to show you how that works in a second, so that we address and access information by a name of a block, not by the location of the block. So literally that block could be anywhere in the world on any connected system that we could get our hands on, and we would be able to pull it in and use it as part of the recipe for a larger volume. We also add a timestamp now to any change in the data. So when someone goes to rewrite a block, we timestamp that change. And you'll see why that's important in just one second. But these are the two things to keep in mind: name, not location, and we've stored time along with that, all rights and modifications. Okay. In the traditional world, back when we were building disk drives that moved and spun, the application would need to know what volume it was writing to. It would need to know what offset it was writing to, what physical location on the disk was being written to. And then it would say, here are the ones and zeros that I would like you to write at that location on the physical disk. As I said, we've broken that mold. So what we've done is we've created a metadata library. I like to think of them as recipes, but we've created a metadata library that keeps track of these blocks that have been written. So let's just say that a block's written at 5:01, sorry, 1 second past 5 o'clock. The application has asked us to write at offset 45, and it's asked us to write specific sets of ones and zeros that you see here. What we do is we create a hash of those ones and zeros, a unique hash, 256-bit hash, that's created by these ones and zeros. So if any of these ones and zeros was to change or be different, it would create a different hash. So this 974D is directly associated only with this set of ones and zeros that you see right here. So in doing that, we have taken the hash and used that as the name for the block, which contains this set of ones and zeros. And we only store that. We only store the name and the data in the global Blockstore. The metadata, as you see here, the database that controls that manages the database, the metadata, actually has the time that it changed. The tag, which in this case, because we're dealing with a block volume, is the volume and offset data, but it really could be anything if it was a different kind of storage mechanism. And the hash, which came from the ones and zeros. So we're storing name and data in this global Blockstore many times. Obviously, for each block of data that's written, we store a block with a name associated with it. Now, let's say at 5:02, the application comes in and it wants to write to volume 3 at offset 03, but it wants to write exactly the same set of ones and zeros. Well, we're not going to go and write another block that has the same hash name. And remember, the hash is directly associated with this set of ones and zeros. So what we do is we make another entry in the metadata library or the metadata database, and we put a pointer in this database to the same block. So we have global organic deduplication. We would never write this block twice. There'd be no reason to ever need to do that. We already have a block that we call 974D that has this particular string of ones and zeros in it. We don't need another one. Okay, let's keep going. Now, let's say at 3 seconds past 5 o'clock, the same application decides that it wants to overwrite what it believes is the data at offset 45 with a different set of ones and zeros. Okay, that's fine. But we don't want to destroy the data. We can't destroy the data that was originally written back here at 501 and then reiterated at 502. We certainly don't want to do that. So we keep this, leave this alone. Nobody touches it. It's fine. It's going to be there. But we will rewrite a new, or we will write a new block of data that has a different hashtag that associates only with this particular set of ones and zeros. And we will call that CB45. So forever, these two blocks will coexist in our global block store, at least forever for now.